So when a solute dissolves in a solvent, an equilibrium process occurs, and it's similar to that of evaporation. Initially, the rate of dissolving is higher than the rate of recrystallizing because there's nothing dissolved to recrystallize. So initially, it's just all dissolving. As the concentration of dissolved ions or dissolved solute increases, some of those particles can recrystallize, and so the rate of recrystallization increases. And so we get a dynamic equilibrium being established. We've got sodium chloride, and it's dissolving, and then the sodium and chloride ions are recrystallizing. Got pictures here. So here's the sodium chloride crystal in water. There aren't any sodium and chloride ions in here initially, and so no recrystallization can occur. We have all dissolving. So we've got the sodium and the chloride ions, and they're dissolving into the water. As they begin to dissolve, and here we see those ion dipole forces, when we've got some that is dissolved, then we can have recrystallization. The recrystallization depends on the concentration of the sodium and chloride ions that have dissolved. The rate of dissolving does not depend on that. So eventually, we'll get to a point where the rate of dissolving is equal to the rate of recrystallization, dynamic equilibrium. When we achieve a dynamic equilibrium like that, that's a saturated solution. So we have dissolved solute in equilibrium with the solid state. If you add more solute, it will not dissolve because the solution is already saturated with solute. If you have an unsaturated solution, that contains less than the equilibrium amount. And so there would not be any solid present, and if you added more solute, it would dissolve until it reached a saturated solution. You can also have a supersaturated solution, which seems impossible. It contains more dissolved solute than the equilibrium amount. Right? How does that happen? Well, it's a little bit like that supercooled liquid that we made in experiment 11A, where we melted those crystals and then we cooled it down below the freezing point. And how should you be able to do that? You shouldn't be able to do that. Well, it's not a stable situation, but it can be done. Supercooled. Here we're talking about supersaturated. A supersaturated solution is unstable, and normally the excess solute will precipitate. So here we've got a supersaturated solution. This is generally, prepared, that's it. Generally prepared by dissolving the solute in the solvent at an elevated temperature, and then allowing it to cool undisturbed without any nucleation sites. So then when we disturb this supersaturated solution, either by touching it with a stirring rod or dropping a crystal in, providing a nucleation site, then the solution realizes, oh, wait a minute, all of this can't be dissolved. It needs to crystallize out, and it will do so very, very quickly. So we're going to watch a couple of videos here. No, that's not working. So this is supersaturated sodium acetate. I'm just going to stick a stirring rod in there, and it's beginning to crystallize. You can say ooh or ah. I never get tired of looking at that. Very, very cool. And here's the other one. Here they're just playing around with it, dipping in toothpicks. It looks like cotton balls with solid sodium acetate. And the temperature goes up because the crystallization is exothermic. So it went from like 25 to 52. So it's sometimes called hot ice because it looks like it's freezing, but it's getting warm. It's actually not freezing, it's crystallizing. It's kind of like a soft popsicle in texture. When it gets disturbed, as it hits the plate there, then it crystallizes, and it does so quickly that you can build things with it. It's crazy. Let it touch the beaker, and it'll climb up into the beaker. Just weird stuff. Races. And there they spelled ice. Hot ice.
In a series of experiments.
No, we don't want to listen to that. Anybody have any questions? Try it. Let's try it. We can do that actually. So the solubility of most solids is temperature dependent, and for most solids, when you increase the temperature of the solution, you will increase the solubility. And this is how that supersaturated solution was formed. Now we don't have sodium acetate in this graph here, but this is the solubility, which is often measured in the grams of solute that will dissolve in 100 grams of water. And here we have that graph versus temperature for several different substances. Here's our friend table salt, sodium chloride. Solubility of salt in water does not vary much with temperature. It increases a little bit, but that's nothing compared to some of these. Potassium nitrate goes from around, 13 grams per 100 grams at 0 degrees up to 100 grams per 100 grams at around 54 degrees Celsius. That's an equal amount of solid and water, and it will dissolve. So most of them will increase with temperature. Some of them are linear, some of them are exponential. And then there's this one that's weird, sodium sulfate. Sodium sulfate becomes less soluble at high temperatures, but that's definitely against the trend. So this equilibrium is taken advantage of in a technique called recrystallization. This is where you dissolve a solid and then allow it to recrystallize slowly, and you can form a more pure solid that way. So you form a saturated solution at an elevated temperature, and you allow it to cool very slowly. You're not trying to get a supersaturated solution. You're going to cool it very slowly and allow the crystals to form. And as those crystals form, it's happening slowly, they are going to minimize any impurities that come into the crystal, because it will be at a lower potential energy if the crystal is perfect. And this is an example of some rock candy made by recrystallizing table sugar. Yes?
So is that why the solid in that experiment, the sodium sulfate or whatever, got cloudier?
So what we had was sodium thiosulfate pentahydrate was the initial compound that we melted, and that is formed in a controlled manner, and so it incorporates 5 waters of hydration for every unit of sodium thiosulfate. When you melt that and then allow it to cool quickly, to freeze quickly, the waters of hydration do not get incorporated. And so that changes the appearance of the crystals. It also changes their melting point. So this is something you can do at home. If you're going to do that, though, look up some instructions. I remember trying this as a kid, and it was an abysmal failure. Because if you don't do it right, it won't work, right? You could waste a lot of sugar. Gases are also soluble in water, but their temperature dependence is the opposite. Most gases are less soluble at high temperatures than at low temperatures, so the opposite of solids. We experience this with soda. I grew up in Minnesota and Iowa, where we called it pop, and then I moved to North Carolina, and we called it soda, and so this, I think the author's just going to cover all the bases and call it soda pop, but that just sounds so stupid. So we'll just call it what we call it in California, it's soda. Cold soda is going to retain its fizziness better than warm soda, right? If you pour 2 bottles of soda, one's cold and one's warm, the warm one is going to foam up much more, right? Because as you pour it, the carbon dioxide is coming out of solution. This is significant for oxygen levels in lakes and rivers. Aquatic life depends on the dissolved oxygen in the water, and those life forms are accustomed to a certain level of oxygen. If the temperature is higher, the oxygen level is lower, and that can cause fish and other things to die. So you can get thermal pollution if you have a factory that's dumping, even if it's very clean water, into a river, but it's warm. That can increase the temperature in that region and cause the death of aquatic life. This is why you have to monitor the temperature of an aquarium to keep the oxygen levels correct. Pressure also has an effect on the solubility of a gas. Soda can is pressurized with CO2. There's always a little empty space. Well, it's not really empty, but it appears empty. Little space up here, and that's carbon dioxide under pressure. Because the increased carbon dioxide pressure causes the solubility of dissolved carbon dioxide to increase significantly. When you pop the top and it goes psst, it's releasing the pressure, and the carbon dioxide begins to come out of solution. The soda begins to go flat as soon as you open it. If you open a clear bottle, 2-liter bottle, and watch it, as you take the lid off, you suddenly see bubbles start to come up. You've removed the pressure, and the solubility has decreased, and it's going to begin to come out of solution. If you increase the concentration of CO2, so here we've got an equilibrium between CO2 in the gas state and CO2 dissolved in water. We have CO2 coming out of solution and redissolving. It's a lot like evaporation, but it's not the same. And we're going to push this piston down and cause this volume to be smaller. Well, that's going to increase the pressure of that gas, right? And the pressure of a gas is really its concentration. And now, because there's more concentrated gas here, we're going to increase the rate of dissolving. And that will that increase will remain until we've reestablished an equilibrium between coming out of solution and redissolving. Did that make any sense? It was so clear in my head, and then it kind of came out in a mess. That can be quantified by using Henry's law. So Henry's law says that the solubility of a gas is equal to a constant times the partial pressure of that gas. The constant is called the Henry's law constant. Very creative, right? So here are some selected Henry's law constants. The units here are molarity per atmosphere. We take this molarity per atmosphere and you multiply by a pressure in atmosphere, and you get molarity. The solubility would be in moles per liter. The Henry's law constant will vary depending on the gas, depending on the water, depending on the temperature. And so you definitely do not memorize those. These are for gases dissolving in water at 25 degrees Celsius. key gas here is the partial pressure of the gas. It has to be the partial pressure of that gas, not just the total pressure. They used to sell these things on TV where you could pressurize the 2-liter bottle of soda so it wouldn't go flat as fast, right? And what it did was it just pumped air into the bottle. Well, that definitely increases the pressure, right? But what's going to determine the solubility of CO2 in the soda is the partial pressure of carbon dioxide. And air is only about 0.6% carbon dioxide, so it's very small. And so pressurizing it with air really doesn't do any good. And it's probably why they don't sell those anymore, because they didn't work. Right? So we can do problems like this. Determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. Because what we need is not the total pressure, we need the partial pressure of the oxygen. We also need the Henry's law constant. So we need to go back over here. 1.3 times 10 to the minus 3. So the Henry's law constant, 1.3 times 10 to the minus 3, molarity per atmosphere. That's for oxygen. It says determine the solubility. Well, Henry's law says that the solubility for oxygen is going to equal the Henry's law constant times the partial pressure of oxygen. So we're going to have that constant 1.3 times 10 to the minus 3 molarity per atmosphere times the pressure, and it needs to be the partial pressure of that particular gas, so 0.21 atmospheres. The atmospheres cancel out. So 1.3 times 10 to the minus 3 times 0.21 2.73 times 10 to the minus 4. And that's molarity, moles per liter. So that's moles of oxygen per liter of water solution. Sig figs, it should only have 2. Any questions?